Hi, I'm Shahnawaz. In last lecture, we introduced k-critical graphs. So let us recall what do we mean by a k-critical graph. So we say a graph G is k-critical if chi of G is k. I mean G is k colorable. And second is that if we delete any vertex from G, then the resultant graph must have k minus 1 as it is chromatic number. So in that case, so this should be true, this must be true for all v in vertex of G. So this should be true for every vertex and this little v in G. So if these two conditions are satisfied, then G is said to be k-critical. Now let us prove a theorem which actually verifies certain properties of k-critical graphs. So we have this theorem. So it states that if G is k-critical, then we have the following. So first item is G is connected. G is connected. Second item is the minimum degree of G, which is denoted by delta of G, it is at least k minus. Third item is G has no pair of subgraphs. So G has no pair of subgraphs, say G1 and G2, such that G is their union and their intersection is a complete graph. So this is a complete graph. And finally, the fourth item is if we remove any vertex, this little v in G, so this is connected as well. This is connected for every vertex v in G. So this is true if provided this capital G is this provided k is bigger than 1, strictly bigger than 1. So in that case, G minus V is also connected. So let us prove first item. So this is our hypothesis. So we are given that G is k-critical. So first we will prove the first item, i.e. we have to prove this G is a connected graph. So proof. So this is the proof of first item. So assume G is not connected. So we'll assume otherwise. So assume G is not connected. So if G is not connected, so it must have at least two components. And earlier we have defined if suppose G is a disconnected graph with suppose m component is G1, G2, so on Gm, then chi of G is actually the maximum of chi of, this is actually maximum of, is actually maximum of chi of Gi, where this I runs between 1 and m. So this means if G is not connected, then it has at least two components. So since G is k critical, so chi of G must be equal to k, because G is k critical. So since chi of G is k, then there is some component, then G has a connected component G1 such that its chromatic number is k. So this follows by this definition over here. Actually, if G is disconnected, so its chromatic number is maximum of chromatic number of the connected components. So if G has chromatic number k, given that G is not connected, so it must have some connected component, say G1, whose chromatic number is k. Now let us consider a vertex V in G which is not in V1. So let V be a vertex in G such that V is not a vertex of G1. So this vertex V is in some another component of G. This implies that then G1 minus V. Now since V is not in G1, so by removing of this vertex, its chromatic number remains unaltered. So then G minus G1 so one can note here clearly G1 minus V let us do this way. So clearly G1 is a subgraph of G minus V, because this V is not in G1, so G1 is actually a subgroup of G minus V. Therefore chromatic number of G minus V, this is equal to chromatic number of G1, which is actually equal to K. because G1 is a subgroup of G minus V. So this follows that this chromatic number of G minus V is chromatic number of G1, which is equal to K. So we have exhibited this subgraph G minus V whose chromatic number is K as well. So this contradicts the fact that G is K critical. For G to be K critical, G minus V must have K minus 1 as it is chromatic number. So we have proved it is this G minus V has chromatic number K. So this is not the case. So this contradicts the fact that G is K critical. Hence our assumption is wrong. So this means that G must be connected. Hence G is connected. Let us prove the second item. So we have to prove that the minimum degree of G is K minus 1. So let us write here this where delta G is the minimum degree. So this is the minimum degree of G. So we have to prove the minimum degree of G is at least K minus 1. Suppose it is a degree is, so let V be a vertex in G such that degree of this vertex V is less than K minus 1. So what we have to prove? We have to prove every vertex V has degree at least K minus 1. I mean it is either K minus 1 or bigger than K minus 1. Now we have assumed here on a contrary basis that it is degree, there is a vertex V in G whose degree is less than K minus 1. Now let us see what we will end up with. So since G is K critical, that means there is a subgraph, therefore the subgraph G minus V, so it has to be K minus 1 chromatic. So has, so this is G minus V is K minus 1 chromatic. Now so this is our assumption here, that is degree of V is less than K minus 1. This is same as degree of V is less or equal to K minus 2. So this vertex V has at least K minus 2 neighbors. So since V has at most K minus 2 neighbors, now one can note here degree of vertex V is less than K minus 1, or degree of V is less or equal to K minus 2. So at most v has k minus 2 degree. Now if v has k minus 2 degree, that means v has at most k minus 2 neighbors. So these have k minus 2 neighbors. So these neighbors of v in G, they use k minus 2 colors. These, since v has at most k minus 2 neighbors, these k minus 2 neighbors, they use at most k minus 2 colors in the k minus 1 coloring of k minus 1 coloring of G minus V. So this is our assumption. So our subgraph G is k critical, that means this vertex G minus V is k minus 1 chromatic. So among these k minus 1 colors, k minus 2 colors are used by the k minus 2 neighbors of V. Now let us color this vertex V with another color. Now color V with the unused color, with the unused color. And now once we color vertex V with unused color, we obtain a k minus 1 coloring of G. So we obtain a k minus 1 coloring of G. So this is a contradiction, since G is k chromatic, i.e. the least number of colors that we use to color the vertices of G is exactly k, not k minus 1. So this contradicts the hypothesis that chi of G is k. Hence every vertex V has degree at least k minus 1. Hence every vertex has degree at least k minus 1. So this proves the second item. Now let us move to prove third item. Now we had to prove G has no pair of subgraphs G1 union G2 such that G is their union and their intersection is a complete graph. So we assume on contrary that G has one such pair of subgraphs. So let G1 and G2 be the subgraphs of G such that G is their union and their intersection is some complete graph, say k, suppose k I mean their intersection is a graph on I vertices, or let us say m vertices. I mean their intersection is a graph on m vertices, which is actually a complete graph. Now since G is k critical, so this is our hypothesis. Since G is k critical, this means therefore G1 and G2, so actually chi of G is k, and chi of G minus V is k minus 1. So now G1 can be a vertex and G2 may be another graph. So these two conditions will give us that chi of G1 is less or equal to k minus 1, and chi of G2 is again less or equal to k minus 1, because of this condition here. That is, if we remove a vertex V from G, it is chromatic number reduces to k minus 1. So in case if G1 is just a single vertex, so it is chromatic number is 1, which is less or equal to k minus 1, because k is bigger than 1. And chi of G2, which is actually G minus G1, while G1 is a vertex, so it is chromatic number is again k minus 1. So therefore G1 and G2 have chromatic number at most k minus 1, have chromatic number at most k minus 1. Now let us consider a k minus 1 coloring of G1. Now consider, so to color the vertices of G1 such that no two adjacent vertices get the same color, we need at most k minus 1 colors. So if we are given k minus 1 colors, we are good. So there is this possibility that if we have less than k minus 1 colors, we can also get we may also get a that number of coloring. But as far as k minus 1 is concerned, we always have a k minus 1 coloring of G1 as well as G2. Now consider a k minus 1 coloring of G1 and k minus 1 coloring of G2. So we can color both the subgraphs with k minus 1 colors. As G1 intersection G2, so this is given to be a complete subgraph. As G1 intersection G2 is complete, so this is complete. So in overlap, so this is our G1 and G2, and this is their intersection. So in this overlap, so when we consider these vertices as the vertices of G1, they may have one coloring, But if we consider these vertices as the vertices of G2, we may have a different coloring. So now to take care of this situation, what we do, we recolor the vertices of either G1 or G2 such that these vertices have the same coloring in both cases, i.e. if we consider these vertices to be the vertices of G1 or to be the vertices of G2, so in both cases they get the same coloring. So in overlap, every vertex in G1 intersection G2 has a different coloring in each of the k-1 colorings. Every vertex of G1 intersection G2 has may have a different coloring in every vertex of G1 intersection G2 may have a different color in the k-1 coloring of G1 or k-1 coloring of G2, k-1 coloring of G1 and k-1 coloring of G2. Now what we do, so actually this implies that the colors in the k-1 coloring of G2 can be arranged such that it assigns the same color to each vertex in G1 intersection G2 as it is given by the coloring of G1. So let us pen this down. So this implies that colors in the k-1 coloring of G2 can be rearranged in such a way that it assigns the same color to each vertex in G1 intersection G2 as is given by the k-1 coloring of G1, as is given in the k-1 coloring of G1. Now combining these two colorings, this produces a k-1 coloring of G, which is not the case as G is k chromatic. Combining, so one should note here that the k-1 colors used in G1 are the same colors used in the k-1 coloring of G2. So combining these two colorings of G1 and G2, we get a K minus 1 coloring of G. This is not the case. This is not the case, since chi of G is K. Thus no subgraphs of the type G1 and G2 exist. Now finally we have to prove G minus V is connected for every vertex V in G where K is given to be equal to bigger than 1. So finally we have the fourth item. So what we have to prove? We have to prove G minus V is connected for every vertex V in G. So we assume on contrary that that G minus V is disconnected for some vertex V in G. So if this is disconnected, then G minus 1. So if this is disconnected, it has at least two components. Then G minus V has a subgraph, say H1 and H2 with H1 union H2 to be equal to G minus V and H1 intersection H2 an empty set. So if this is the case, so let G1 and G2 be the subgraphs. So G1 is a subgraph. Actually this is induced subgraph on the vertices of H1 and V, and G2 is the induced subgraph on the vertices of H2 and V. So let G1 and G2 be the subgraphs induced on H1 and V, so that G1 be the induced subgraph induced on H1 and V, and G2 be another subgraph, obviously the subgraph of G induced on H2 and V. So then what we have then G is actually union of G1 and G2, and G1 intersection G2. So since H1 and H2 they are empty, so G1 and G2 they must have only one vertex in common, because G1 is a subgraph induced on H1 and V, and G2 is a subgraph on induced subgroup on H2 and V. Now H1 and H2 they have nothing in common, so this V will be the common vertex here in G1 and G2. So this G1 and G2 is actually a single vertex. A single vertex is nothing but K1, a complete graph on a single vertex. So let us write here where K1 is a single vertex. So a single vertex can be identified as a complete subgraph on one vertex. So this is a single vertex. So this is not true, since we have proved in item 3 that no such subgraphs exist. So this is not possible as proved in item 3. Hence G minus V is connected graph for every vertex in G, for every vertex V in G. So this proves the theorem.